Good morning, Professor Darren. I'm Haina Chuan, and today I'm going to do my presentation. The topic is about why every sequence has a monotone subsequence. Okay, let's start. First, I'm gonna show you the content. The content is here. Before starting our topic today, I'm gonna briefly introduce 3 points. First is about the convergence of sequences, it's a definition. And second is about why every convergent sequence is bounded. And the third is about the monotonicity. This is all very useful. Okay, this is all very useful in the fourth point, why every sequence has a monotone subsequence. Now here we go. Section 1. Convergence of subsequences. I think that this definition is very familiar with us after this semester. Okay, so a sequence AN, we can find a sequence AN. It is said to converge to the number A, provided that for every positive number epsilon, there is an integer, big N, such that an minus a is smaller than epsilon, and for all small n which is bigger than the big N. Okay, this is a definition, and I think it is very familiar. Let me show you. Okay, so this is a text. All right. Section 2. In Section 2, I'm gonna talk about why every convergent sequence is bounded. We can just set a sequence, still AN, okay. We have a sequence AN, and we can let it be a convergent sequence, convergent. And because it is a convergent sequence, so we can assume that it can converge to a unique limit A, converge to a unit limit A. And then we can give epsilon which is bigger than 0, and then there exists a small m. There exists a small m in the big N. We're given epsilon which is bigger than 0. Okay. Then we can find such that an minus a is smaller than the epsilon, and the small n which is bigger than the big M. Okay, and big M equals to the maximum number of a1 minus a2 minus a, an minus a. And then we can find that an minus a, it must be smaller than this number, m plus 1, for all n, for any small n, okay? So from this step, we can imply that an minus a is in this interval, minus m minus 1 and m plus 1, okay? And finally, we can find that an is bounded, and an is in this interval, small a minus big M minus 1, a plus m plus 1. Okay, definitely an is bounded from above. Okay, so hence every convergent sequence is bounded. So now let's take a look. Right, convergent sequence to limit A. Okay, next section. Section 3. Section 3 is about the monotonicity. And as we all learned before, a sequence is said to be monotonically increasing, and another sequence can be said to be monotonically decreasing. And the sequence an is called monotone if it is either monotonically increasing or monotonically decreasing. Let's take a look. First, a sequence an is said to be monotonically increasing, provided that for any an plus 1 is bigger than an, right? Monotonically increasing. This is an, and this is an plus 1. It is very, very straight to see, okay? Very clear. And the sequence an is said to be monotonically decreasing, provided that an plus 1 is less than an for any n. So this is just on the contrary to the increasing. It's like this. I mean, this should be an plus 1, and this should be an. When n is getting bigger, an is getting smaller. Okay. A sequence like this is said to be monotonically decreasing. And a sequence an is called monotone if it is either monotonically increasing or monotonically decreasing. Now, let's start the section 4. Now, from above, we all know the definition of a convergent sequence. And we all know that why every convergent sequence is bounded. And we also know that the monotonicity of sequences. So now we can begin our topic. Why every sequence has a monotone subsequence? Still, we can just given a sequence Sn here, and then we have two conditions. Sn is bounded or not. Sn is bounded or Sn is not bounded. Two conditions. Bounded or unbounded. Okay, so if Sn, the sequence Sn is unbounded, then the result follows. Yeah, the result will follow. Let me show you. And if Sn is bounded, then there exists a convergent subsequence. And we can call this convergent subsequence maybe An, okay? This is a convergent subsequence. And we can suppose that the limit of An goes to P equals to P. Okay. The limit of An equals to P. And if infinitely many of the terms of An are equal to P, then these terms of An, they can form a monotone subsequence. Actually, it's a constant subsequence. If not, then either the two interval P minus 1, P, or the interval P to P plus 1 must contain infinitely many terms of An. Okay, let's see it. Let Sn be a sequence, and we have two conditions, as it is bounded or not. If it is bounded, if it is unbounded, or it is bounded, then we can have a convergent subsequence An. And yeah, these terms of An, they can form a monotone subsequence. Here we go. So now we have two intervals. We choose these two intervals. These two intervals, one of them must contain infinitely many terms of An. And the case 1 is we suppose that this interval P minus 1 to P contains infinitely many terms of An. And we select one of them and we say An1. Okay, we say An1. And because that the limit of an equals to p, then there must be infinitely many terms of an in the interval an1 to p. You get the point? Yeah. Because we select one of them. So, and there must be infinitely many terms of an in this interval. Okay, because it is infinitely many terms. And we can select a term an2 in this interval. And n2 must be bigger than n1, okay? So, in general, having obtained an2, we may select ank plus 1 in the interval ank to p. Ank plus 1 in the interval ank to p. Okay, with nk plus 1 bigger than nk. Right? This is clear. Okay, here we go. In this way, we can obtain a monotone increasing subsequence ank of an that converges to p. Okay, since an is subsequence of Sn, then ank is also a subsequence of Sn. So every sequence has a monotone subsequence. Okay, this is just case 1. We still have a case 2, you know. We have two intervals. And in case 1, we suppose that this interval contains infinitely many terms of an. And in case 2, we will suppose that the interval from p to p plus 1 contains infinitely many terms of an. And you know, it's actually the same. It's actually the same. Let's take a look. We can suppose that p to p plus 1, this interval contains infinitely many terms of an, and we select one of them, and we say an1 prime. Okay, since the limit of an equals to p is still the same, right? Then there must be infinitely many terms of an in the interval p to an1 prime. You get me? Now this time it's all different from the case 1. Okay. Then we select a term an2 prime in this interval. N2 prime, it belongs to this interval. Okay, and n2 prime must be less than n1 prime. And in general, having obtained an2 prime, we may select ank plus 1 prime in the interval p ank prime. Can you get the point? Okay. And of course, here the nk plus 1 prime is smaller than the nk prime. So in this way, we obtain a monotone increasing subsequence ank prime of an that converges to p, right? And since an is a subsequence of Sn, so ank prime is also a subsequence of Sn. And from all above, we have shown that every sequence has a monotone subsequence. So now here comes a question. What else method can we use to prove that? To prove this? You know, this is only one method. And I'm sure that we have some, other methods. Right? So now maybe I can show you another method to do this. Okay. We can call a positive integer n. A positive integer n. It is a peak index. A peak index. If k is bigger than n and ak is smaller than an. So there are only finite. So we have two cases, right? We still have two cases here. We also have two cases here. The first case is there are only finitely many peak index. And the case 2 is, I'm sure you know that, there are infinitely many peak index. Okay. So in case 1, we can let the big N to be the largest peak index. So any small n which is bigger than n is not a peak index. N is not peak index, okay? So there exists n2 is bigger than n1, satisfies an2 is bigger than an1, okay? And there exists n3 which is bigger than n2, satisfies an3 is bigger than an2, okay? So we can have a subsequence. We can have a subsequence here, an, an2, an1, an2, an3, and that is increasing. Okay, that is increasing. And it is a, it is a increasing subsequence. Okay, so when they are in case 2, there are infinitely many peak indexes, indices. Okay, so now here we can have n1 is smaller than n2 is smaller than n3, smaller than da 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 da, and an1 is actually bigger than an2, is bigger than an3, is bigger than da 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 da. So here, an is a decreasing subsequence. An is a decreasing subsequence. So now I think that from all above, you must be very clear why every sequence has a monotone subsequence. I've already introduced 2 methods here and some definitions that we are going to use in the proof. Okay. So I think so far I have finished my presentation. Thank you very much.